Welcome to the Explainer, everyone. Okay, so today we're tackling something that, might sound a little like dry physics at first glance, but honestly, it's actually one of the most high-stakes engineering quests in human history. We're talking about the literal key to unlocking deep space exploration. When you watch a rocket launch, you see this massive roaring pillar of fire and smoke, right? But beneath all that incredible brute force is this really quiet, rigorous, mathematical battle for efficiency. So let me ask you something right off the bat. What makes a rocket truly efficient? We kind of tend to confuse the spectacular, ground-shaking power of a rocket leaving the pad with how well its engine is actually performing. But raw power doesn't necessarily mean smart power. To push the boundaries of space travel, engineers literally have to look past that sheer propulsive force and focus entirely on the actual efficiency of the engine. To really understand why this is such a big deal, we gotta look at what's called the rocket mass problem. The stark reality of rocket engineering is that propellant constitutes the absolute largest fraction of the total launch vehicle mass. A rocket is severely restricted because the vast majority of its weight is just the fuel and oxidizer it needs to get moving in the first place. Imagine, for a second, if you had to fill your car's entire back seat, the passenger seat, and the trunk with gas just to drive across town. Crazy, right? Well, that is the everyday reality for rockets. So here's our roadmap for today's explainer. We'll start with the rocket mass problem, then we'll define specific impulse. After that, we'll look at what actually drives engine efficiency, compare thrust versus specific impulse, and finally, check out the engines of the future. All right, let's jump straight into part one, the rocket mass problem. So because we're forced to carry so much heavy fuel, it triggers this whole cascade of limitations. This massive weight severely limits our payload capacity, which basically means smaller satellites, fewer scientific instruments, or, fewer astronauts. It also caps our mission duration and just makes space travel broadly inefficient. If we want to build a moon base or send humans to Mars, we absolutely can't just keep building bigger tanks and adding heavy fuel. We desperately need to utilize the propellant we do carry much, much more effectively. Which brings us nicely to section 2, defining specific impulse. This is where we meet our hero metric, specific impulse, or ISP for short. It's officially defined as the thrust produced per unit weight flow rate of propellant. Basically, it's the ultimate efficiency index of a rocket engine. Now, if you're trying to wrap your head around that dense engineering definition, just think of it as the miles per gallon for a rocket. It's really that simple. Just like a car with higher MPG goes further on less gas, a rocket engine with a higher specific impulse gets you greater thrust for the exact same amount of propellant. Let's actually look at how this builds mathematically, because it's quite elegant. The equation is ISP equals F, divided by m dot times G0. Don't worry, it's straightforward. The numerator, F, represents the thrust, the actual push being generated by the engine. And the denominator represents the weight flow rate of the fuel being consumed. So it's simply how much push you get divided by how incredibly fast you're burning through your heavy fuel supply. Now here's where it gets kind of wild. When you run that math, something really interesting happens with the units. Because you're dividing a force by a weight flow rate, the force units mathematically cancel each other out. And what we are left with is a slightly bizarre but incredibly crucial unit of measurement: seconds. Yep, you heard that right. The efficiency of a rocket engine is quite literally measured in time. So, what does that actually mean in the real world? Well, it indicates the duration for which 1 unit weight of propellant can produce 1 unit of thrust. And this brilliantly illustrates the core concept here. A higher number of seconds means better engine efficiency. If engine A has a specific impulse of 250 seconds and engine B has 350 seconds, engine B is vastly superior. Why? Because it consumes way less propellant to generate the exact same amount of thrust. All right, moving on to section 3, what drives engine efficiency? Under the hood, propulsion engineers have a few specific levers they can pull to optimize this performance. The major factors affecting specific impulse are the exhaust velocity, the specific type of propellant used, the pressure inside the combustion chamber, how efficiently the nozzle is designed to convert thermal energy into kinetic energy, and finally, the ambient pressure of the environment the rocket is actually flying in. Now, among all those factors, exhaust velocity is an absolutely massive driver. Mathematically speaking, specific impulse is directly proportional to exhaust velocity. So if engineers can figure out a way to make the hot gases shoot out the back of the rocket faster, they directly increase the propulsion efficiency and lower the overall propellant consumption. Basically, faster exhaust directly equals higher efficiency. It's a one-to-one win. But of course, there's a catch based on where the rocket is currently flying. Ambient pressure changes things dramatically. When a rocket is sitting down on the launch pad, the sick Earth atmosphere is literally pushing back against the exhaust. This is exactly why sea level specific impulse is always lower. But once that rocket climbs up into the vacuum of space, atmospheric pressure is pretty much negligible. The exhaust can expand much more freely, resulting in a significantly higher vacuum-specific impulse. So rockets are quite literally more efficient in space than they are right here on Earth. Let's dive into Section 4, Thrust versus Specific Impulse. We really need to clearly contrast these two metrics because they get mixed up a lot. Thrust is the raw force produced, measured in newtons. Its one and only job is to accelerate the rocket and fight gravity. Specific impulse, on the other hand, is your propulsion efficiency, measured in seconds. Its job is efficient fuel utilization. To put it as simply as possible, thrust is what gets you off the launch pad, but specific impulse is what dictates how far you can go once you're actually moving. So the crucial point here is this fundamental classic engineering conflict. If an engineer wants more thrust, they generally have to dump more fuel into the engine at a much higher flow rate. But maximizing specific impulse demands the exact opposite: careful, highly efficient propellant utilization. Honestly, a propulsion engineer's entire job is basically a high-wire balancing act between these two totally conflicting objectives just to achieve optimum performance for a specific mission. Which brings us to our final section, engines of the future. As you can see, there is a massive range of efficiencies across different propulsion systems. A conventional solid rocket motor, kind of like the boosters on the space shuttle, has a relatively low specific impulse, usually topping out around 290 seconds. But as we move up to cryogenic rockets, which use supercool propellants like liquid hydrogen and liquid oxygen, we jump up to around 465 seconds. And then, look at the bottom of the list. Nuclear, thermal, and ion thrusters push those numbers way up into the thousands. When you visually compare these systems side by side, the sheer gap is just staggering. An ion thruster's massive 5,000 seconds of specific impulse is honestly incredible. Now keep in mind, electric propulsion systems like this produce very, very low actual thrust. Like, they couldn't even lift a tiny model rocket off the Earth. But their fuel utilization is so incredibly efficient that once they are up in the vacuum of space, they can run for months or even years, slowly but surely accelerating spacecraft to mind-bending speeds. Okay, let's bring this all back to the real-world stakes for a second. Why does optimizing this single, slightly weird metric matter so much? Because specific impulse is the absolute primary criteria engineers use to select propellants, compare engines, and ultimately design these massive space missions. Every single extra second of specific impulse means less fuel, which directly translates to increased payload capacity, way longer mission durations, and massive, massive reductions in launch costs. When we're talking about long-duration interplanetary missions, propulsion systems with high specific impulse aren't just preferred, they are absolutely required. You simply cannot drag thousands of tons of extra fuel all the way out to Jupiter or Saturn. It just doesn't work. Packing light and flying efficiently is literally the only viable path forward for deep space exploration. And that leaves us with this final thought to ponder. We often dream about where humanity is going to go next, right? Mars, the outer planets, maybe even other stars someday. But as we aim for those distant horizons, remember that our ultimate reach into the cosmos won't just be dictated by sheer willpower or big explosions. It will be dictated by our ongoing quest for extreme engine efficiency. As we engineer higher and higher specific impulse, which distant star system do you think will reach first? Thanks so much for joining me on this explainer, and as always, keep looking up.